Hi, welcome to today's session. I am Balakrishnan from CAC department. Today's topic is on computer architecture. So that first let us discuss about some of the gate questions. First question is about the speed of supercomputer, how it is measured. So that I have given four options. Option A, kbps, option B, mbps, option C, flops, and option D, MIPS. So which is the option for the supercomputer to measure the speed of the supercomputers? Certainly that whenever you want to study about that one, so this is the thing that answer is option C. Why that option C we are getting is floating point operations per second. It is called as flops. Okay, so it's a measure of computer performance based on the number of floating points. Okay, so arithmetic calculation that the processor can perform within a second. So whenever we are doing that, it's a term used in computing here in the particularly whenever in the computer architecture, it's a measurement for using that. So calculation carried out the floating point representations of the particularly of the real numbers. Okay. So next question 2 is about the daisy chaining. Daisy chaining is used to assign priorities in attending interrupts. When a device raises a vectored interrupt, the CPU does polling to identify the source of the interrupt. In polling, the CPU periodically checks the status bits of no if any device needs its attention to know that. During DMA, both the CPU and the DMA controller can be bus masters at the same time. So these are some of the things. Let us see the questions here. Okay. So the question, what are the options here? 1 and 4 only, 1 and 2 only, C3 only, option C, and option D is 1 and 2 only. So let us see what is the answer here. So answer here, the answer D. Why we are selecting the answer D? Before going to discuss about that, we will see what are the statements of whatever the option statements. Okay, to determine which of the given statements are true, let's analyze each one individually. So statement 1, daisy chaining is used to assign priorities in attending the interrupts. So whenever we want to attend the interrupts, we have to use the daisy chain concept. So daisy chaining is, what is that? It will be doing the interrupt handling. Daisy chaining is a method used to assign priority to devices requesting it. So many devices will be there in the computer. So whenever they want to have the attention, they have to send in the interrupt. How to handle that? That is done by daisy chaining. So devices are you know that devices are connected in a series by configuring in a series, and then it is connected in a chain. That's why it's called as daisy chain. Okay. So here that the interrupt acknowledge INTA, that second thing is passed from one device to the next in the chain. Okay, so a device with the higher priority is placed closer to the CPU, and so it receives the interrupt signal from that, interrupt acknowledgement signal from that. This method allows the CPU to service higher priority devices before lower priority ones. So conclusion, this statement is true. Let us see the next one. Okay, statement 2, when a device raises a vectored interrupt, the CPU does polling to identify the source of the interrupt. So what are the analysis here? Vectored interrupts. Okay, the vectored interrupt. In a vectored interrupt system, each interrupting device is assigned a unique interrupt vector here. So that, what about this one is, here the interrupt vector typically contains the address of the interrupt service routine. What in the routine, interrupt service we are giving, it will be specific to the device. When a device raises a vector interrupt, it provides its interrupt vector to the CPU automatically. The CPU uses this vector to directly jump to the appropriate ISR without needing to identify the source. Okay, so this one. So polling, next one is polling. Polling involves CPU checking each device's status status register to determine which device needs attention. Okay, that polling, whenever we do the polling, it will be some kind of attention is required for the particular device or something. Okay, poll is typically used in non-vectored interrupt system or when interrupts are not used. Wherever the interrupts are not used, this one is done. So next one, conclusion. Statement 2 is false. Why we are telling the statement 2 is false is, in vectored interrupts, the CPU does not perform polling to identify the source. The device provides the necessary information directly. So that is the reason. So statement 3, in polling, the CPU periodically checks the status bits to know if any device needs its attention. This one, the statement 3 tells about that one. So here the analysis of the statement 3, polling mechanism. Polling is a technique where the CPU periodically checks the status register of peripheral devices. Whatever the peripheral devices connected to the system, it will be reading. The CPU reads the status bits of to determine if a device is ready for transfer or required service. Whatever the transfer of the other service is required by that. This method is simple but can be inefficient. Why? Because the CPU spends time checking devices even they do not need service. So what it happens is, it will be checking this for some service. Whenever it is not required time also, it will be doing that. So that conclusion, what is the conclusion here is, the statement is true. Okay. So next one, statement 4, during DMA, both CPU and DMA controller can be bus masters at the same time. What is the analysis of that? So you know that DMA is direct memory access. DMA allows device to transfer data directly to or from memory with the continuous CPU intervention. Okay, so that by entering computer, whenever the memory is required, it will be doing that. The DMA controller temporarily becomes the bus master. Okay, bus master to control the data transfer. It does like that. So here that the next one is question 3. A CPU has 24-bit instructions. It is a byte addressable memory. A program starts at the address 300 in decimal, which one of the following is a legal program counter. All values will be in decimal. So what is option A is 400, option B is 500, option C is 600, and option D is 700 has been given. So that first that the question is, CPU has 24-bit instruction. It is these are the values have been given. It is a byte addressable memory and a program starts at address 300 in decimal. Okay. So whenever see that the answer is option C. Why the explanation of the answer is why we have why it is the option C answer is, each address is multiple of 3. Okay, so as the starting address is 300 and each instruction consists of 24-bit, that is 3 byte. Okay, so thus in the given options of the valid counter will be one of which is a multiple of, always will be a multiple of 3. Out of the options we can see that only 600 satisfies the condition. So the option we have, so that therefore the option C is the answer here. So next one, question number 4. Which of the following addressing modes are suitable for program relocation at runtime? So you know about that whenever the addressing mode, the program relocation is required, whenever at runtime it is required. So here 4 options have been given. It may be absolute addressing or based addressing or relative addressing or incorrect addressing. So what are the things required? Let us see about option 1 and 4, or option A is 1 and 4, option B is 1 and 2, option C is statement 2 and 3, option D is statement 1, 2 and 4. So what will be the answer? You got to know. So here whenever the option here is C, so let us see about what are the statements. The based addressing. What is based addressing? This mode uses the base register that holds the starting address. Base register will be holding the starting address and the instruction contain an offset relative to that base. That whatever the offset relative to that base it will be having, allowing the program to be loaded at different memory location without modifying the code itself. So without modifying the code itself, how it can do that? Okay. Next one is relative addressing. Here addresses are calculated relative to the current program counter. So meaning that the instruction can reference locations regardless of where the program is loaded in the memory. whatever where the program is loaded in the memory, not regarding with that. Okay, so here whenever the absolute addressing, what is the definition for that? This mode uses fixed memory addresses, making it unsuitable for relocation, as the program need to be loaded at the exact same memory location every time. So some kind of things may be loaded like that, the exact where it has to be stored, there we will be having that one. Next one is indirect addressing. While not directly related to relocation, this mode uses an address stored in the register to access the actual operand. So this is so that's what we are having. The question number 5: which of the following is not a form of memory? So here 4 options have been given: instruction cache, instruction register, instruction opcode, and translation look aside buffer. So here that what is the answer is instruction opcode. Why we are giving that this thing is, let us see about that one. So next one is question 6. An instruction format has the following structure: instruction number, opcode destination. Next one is source register 1, source register 2. So here we have some kind of instructions have been given continuously, the pipeline processor, how it is going. The following sequence of instruction to be executed by the pipeline processor. So instruction 1, instruction 2, instruction 3 and instruction 4. What will be the instruction 2? That division of R3, R1 and R2. Subtract of R5, R3 and R4, addition of R3, R5 and R6, and instruction 4 is multiplication of R7, R3 and R10. Which of the following statement is are true? Okay, so whenever we are speaking it and the answer instruction to opcode, sorry. So there is a raw dependency on R3 between instruction 1 and instruction 2. There is a war dependency on R3 between instruction 1 and instruction 3. There is a raw dependency on R3 between instruction 2 and instruction 3. There is a wow dependency on R3 and R4. So whenever we are speaking like that, so question 6 that sorry. Answer option A. We are a pipeline processes. We are discussing about each option. A pipeline processor processes multiple instructions simultaneously at different stages of their execution. Understanding data dependencies in this context is crucial for identifying the potential hazards, whatever the things. The common types of dependencies are read after write, write after read, war, this is called as war, and write after write, that is wow. So let's analyze each of the given instruction. So division, whatever the division of the R3, R1 and R2 register, or subtraction of the according to the instruction 2, instruction 3 and instruction 4, whatever the things we have to see is, let us see. Now let's evaluate each statement. Option A, there is a raw dependency on R3 between instruction 1 and instruction 2. Okay, so read after write, what dependency occurs when an instruction depends on the result of a previous instruction. Here instruction 2 reads R3 which is written by instruction 1. Thus there is a raw dependency between instruction 1 and 2, that whatever the that read after write dependency is there. So this statement is true. Option B, there is a war dependency on R3 between instruction 1 and instruction 2. So here what write after read option, okay, dependency occurs. Why it is occurring is when a later instruction overwrites the register that a previous instruction reads. In this case there is no war dependency as instruction 3 writes to R3 which instruction 1 also writes it but not reads from. So this statement is false. Option C, there is a raw dependency on R3 between instruction 2 and 3. This statement examines if instruction 3 reads R3 which is previously affected by the instruction 2. Okay, so however instruction 3 reads R5 which is the output of instruction 2. So but writes to R3. Thus there is no raw read and whatever the raw dependency on R3 between instruction 2 and instruction 3. So this statement becomes false. Option D, there is a wall dependency on R3 between instruction 3 and instruction 4, write after write. What are the dependency occurs when two instructions write to the same register? Here I3 writes to R3 and the value of R3 is used by instruction 4. So this is not written by instruction 4. Thus there is no wow dependency. So the statement becomes false. So question 7, okay, let the WB and WT be suit set associated cache organization that use LRU algorithm for cache block replacement. WB is a write back cache and WT is a write through cache. So which of the following statement are false, whatever the things. So let us see about the answer for this. Each cache block in the option A is each cache block in the WB and WT has a dirty bit. Each option B is every write hit in WB leads to a data transfer from cache to main memory. C, eviction of a block from WT will not lead to data transfer from cache to main memory. Option D, a read miss in WB will never lead to eviction of a dirty block from WB. So let us see about that. Option B, know that what about the write back cache. Okay, write back cache, what is that? Update the cache block, do not result updated to the main memory immediately. So burst writes are preferred for higher throughput. The burst writes, whenever the burst writes, we get more throughput from that, and those needed higher writing performance. We can write more things in that memory. So that write through cache, that is the concept that called update to the cache block or reflected on the main memory. Whatever we are updating, it should be reflected on the memory before carrying out the process, consistency process. Whenever we want to handle that we have to do that. Okay, so here whenever we are seeing that, so a dirty bit is necessary for WB in order to avoid the redundant writes to the main memory, but it is not required in WTS. All changes are reflected after write operation is done. So this statement is false. Next, the temporary use of WP cache memory is to increase the throughput and for the speed mismatch between main memory and processor. However, when the multiple writes are done for the same cache block, what happens? These are not reflected immediately, because so every hit in the WB does not necessarily lead to the data transfer from cache to the main memory. So this is the concept you see. So it becomes, according to that, this concept is false. Next, C, option C, the goal of the WT cache is to maintain the consistency override performance, while as the cache block is used to reflect the changes to the main memory. So this option is becoming the true option. Okay, true option. There are truth statement, there are replacement strategies in LRU. Okay, so the LRU for dirty and regular blocks, which means that a read miss might or might not remove a dirty block. So that we have to. So hence the correct correct options are A, B, and D. Okay, thank you. We'll see you in the next session.